Great. That was yours. Sorry, I just shut down thinking it was my phone. Straight away, interfering. Oh, sorry.
You just think about what you're doing, all right? Think very carefully about what you're doing.
Thank you very much. Remember this, Sam? I think you'll be impressed that.
I remember starting.
Great. Okay, I think I've got the all clear to go. Good evening, everyone. Hello, hello. Can we hear me? Should I speak a little louder? Good evening and welcome to this very exciting event. Thank you for joining us on this special occasion. It is my great pleasure to welcome you to the inaugural lecture of Professor Sam Lucas. My name is Becky Lucas and I'm the Head of People and Culture for the School of Sport, Exercise and Rehabilitation Sciences, where Sam is a part of. I'm a colleague of Sam's and I'm also a very proud sister. So in each of those capacities, that's why I'm here today to introduce Sam and to welcome you to his inaugural. It's great to see so many people here. Thank you for making the effort. And thanks especially to those who have travelled up to see Sam speak today, or down, as it may be. Particularly, I'd like to thank the people who are signing in online and those who are joining us from New Zealand today, where it is actually 3 a.m. in the morning. So if they've managed to do it, props to them, and we welcome you and thanks for being here. I'd also like to take a moment to acknowledge some very special guests who've made it here today. First up, our parents, Mum and Dad, Anne and John, for those who want to say hi afterwards. They've travelled over from New Zealand to be here today, so welcome. Also, I want to say hi and acknowledge Sam's family, his partner and wife, Kristen, who's up the back there, taking notes, and also his 3 kids who are behaving very well. Back there, we've got Jay, Henry and Ruby Molly as well. So welcome and it's great to have you on campus and here listening to this event. In terms of introduction, Sam and I are from New Zealand. We grew up on the east coast of the South Island in a place called Sumner, Christchurch, and very close to the beach and near to the mountains. And that's a key part of where Sam's academic journey began. And also his commute to that academic journey began there as well. His love of the outdoors really was inspired and enlivened by where we grew up as well, I feel safe in saying. And probably I would also say, and I have some good authority to back me up on this, that that's the first point where we saw Sam's problem-solving initiative, his natural problem-solving initiative, really come to light in those early days. But I would say Sam's academic journey really began to take shape when he was 18, 19, and he opted to undertake an outdoor education training program over on the west coast of the South Island, and he did that for 2 years, and that was a really important chapter in Sam's life and really started off his love of and engagement with the outdoors in a more official capacity. But from there, he opted to further his education and travel down to the University of Otago, which is in the deep south of New Zealand, where he undertook 2 undergraduate degrees, clever clocks, finished those and went on to complete a PhD and then was successful in securing a postdoctoral fellowship at the University of Otago. And in those degrees, and that positions he was spanning the School of Physical Education and Exercise Sports Sciences, as well as the Department of Physiology there. Then in 2013, Sam and his family decided to make the big leap and move to the UK. And since joining the University of Birmingham, Sam has built a really vibrant interdisciplinary research portfolio that spans the fields of exercise science, environmental physiology, physical activity, and health. And he's also continued to develop really strong collaborative relationships with his colleagues, many of whom are here today, as well as different institutions, organisations, and universities, both within the UK and abroad as well. So this evening, Sam will share with us his story, his journey of his research so far to date. Best is I'm sure, just yet to come. It's always important not to peak too early, right, Sam? And you'll know, no doubt, every confidence that you'll see the energy, the dedication, and the collaborative effort that's really inspired Sam's research. So without further ado, I'd like to welcome Sam. Welcome, Professor Lucas.
Thank you, Dr. Lucas. Thanks, Becky. Yeah, thank you for the introduction. I think I've pretty much finished already, so I covered a number of my slides at the start, which is probably a good thing. But just to reiterate, Becky's welcome. Thank you for coming. Thank you for those that are joining online now and that you do if you watch the recording later. I appreciate you being here, particularly Mum and Dad travelling from New Zealand. It's wonderful to be able to share this moment and celebrate this with you and my family up the back, kids and my wife Kristen, or Bubs as we call her. If that's a slip of the tongue later on, then you'll know that it's a nickname. So my journey through here, Becky's given, I guess, the introduction. What I want to do is talk through, I guess, why I came up with the title of Professor of Cerebrovascular Exercise and Environmental Physiology. To me, those are, I guess, my key areas of interest in terms of my research, and it's also what I teach. So the plan is to kind of move through my career, I guess, on a timeline, but then also thematically to then sort of go through and look at the things that I've done within those themes as I've gone along. So that's my little thread that I'm going to try and use to remind myself, and hopefully you guys might pick up on that as well. And hopefully by the end of it, the alternative title of Why Am I Here will be clear in terms of, I guess, the opportunity and the excitement of the work that you can do here in Birmingham, and why I guess I left New Zealand. And now I've been told that I must have some photos, some family photos, embarrassing children. Becky mentioned already that we grew up in a beautiful little suburb, Sumner. You can see with that arrow, that's where our house is. You know, two blocks from the beach. I'm one of three. I'm the middle child. There's Becky and our big sister, Joe. So Mum and Dad still live there, which is fantastic because we can go back, when we go back to New Zealand, and we can go back to the place which is very special to us, and I can take my kids and they can stand on the beach where I made lots and lots of memories as a kid growing up. Now I have a unique opportunity as a big brother, not only embarrass myself, but be able to embarrass Becky. And I thought what I'd do is I'd take the opportunity to show the early evidence that I have of being a supportive big brother. So whether that's supporting her on her first day of school, or her supporting her in her nutritional options, or even with her fashion choices here in the bottom right. So as Becky mentioned, after I left school, I went and I did outdoor education as a first, I guess, venture into education. But what she didn't mention is that was after 1 year at Canterbury University, where I was studying engineering, which academically didn't go particularly well. But what I did, I guess, find or connect with was a love for the outdoors, particularly kayaking, and that was through our elder sister, Jo, who was the club captain of the university club there, and a very good boater. That's her in the top doing a first female descent of a waterfall or big drop in Norway. And you can see the classical Lucas determined look that she's holding a nice duvet as she goes, drops out of an eddy there. So some photos, I guess, just to highlight what I was doing. My photo albums are in New Zealand, so I relied on other people to send me some photos. So this was an outdoor education course where we were trained and we instructed school children or other groups to go into the outdoors. None of the photos that I have are of any of those formal education settings. They're all of us having fun, which was a wonderful 2 years. And I think it's important to mention, I guess, another moment that happened to me, because it really did shape who I am in terms of growing up. In those 2 years, in 1995, I was part of an event which was a tragedy, I guess, and sadly we lost a number of our classmates, and it was, I guess, something which happened to me and a number of other families that really, I guess, shaped how I am today. We just was in New Zealand earlier in the year for the 30th reunion and caught up with 2 other survivors. They weren't in the fall, but they very much dealt with what was at the bottom. And it was wonderful to catch up with them. And I guess us to share after 30 years and really the first time we were back together to talk about what it has meant for us and for me. And for in my scenario, you know, it's really helped me understand what's important, taught me resilience and how to be determined for me to get over my injuries and return back. And I think that resilience, that determination are key attributes and skills that we need as academics to survive in this setting, which can be pretty brutal sometimes. I won't dwell on that too long, but while I was there, I was challenged. What are you going to do with your life? And this is our head tutor at the time. He looked like he had a fun time at work, and I thought, that's what I want to do. So long story short, as Becky mentioned, I went back to university, having said to Dad, I'm never going back to university, to study physical education, I guess, with the thought of going into outdoor education as a vocation. But along the way, I guess, discovered physiology. Did my BSc in physiology as well, and then went on and did a PhD. I don't have my photo album. I was a bit hesitant to ask friends to send me any photos, but I did have this one, and I think this captures how excited I was to live and experience what it is to be a student in Dunedin. In the end, I got there, and there's a picture of me and my family graduating on that day. So 14 years in higher education, and then I finally got myself a job, which was something that Dad was I'm very keen for me to get at some point in my life. Why academia? I mean, I distinctly remember, I guess, a moment in my undergraduate where the head of the PGR program, Doug Booth, came and said, academia is the ultimate lifestyle. Gives you the freedom to explore your interests, your passions, and the power to change and influence things around you and beyond. And that, I thought, well, this is pretty cool. And I don't fancy getting a job just yet, so I'm going to stay at university and do that. So I enrolled in the honours program and worked with Will Hopkins. And did an honours project there. It's a little different in New Zealand. You have to apply, and I was lucky enough to be selected into that. And Will's a passionate scientist, I think, and a wonderful guy. Our Friday morning meetings were very entertaining. Along the way, I met Jim. Jim had just started at Otago. So when I was returning from my kayaking weekends and was staying in the computer lab until 1, 2 o'clock in the morning, Jim was also there preparing for his lectures the next week. So I think we really struck off a common understanding about time management and passion for our work at the same time. And it's a real pleasure to, I guess, to continue to work and collaborate with Jim. And here's just a couple of examples of how Becky and I guess, are still connected to Jim. We still catch up at conference. Even he's standing there with his wife, Kate, stayed with us and our grad students when we were in ECSS, which was in Paris, and very much still mentors me, you know, and that extends out into our research group. So we're very lucky. And the connection goes further in terms of the fact that he's actually bought, while he was in the UK at that conference in 2023, he bought the house next door to my in-laws. So that's my kids knocking on his door when we were last out in New Zealand. Okay, so that's, I guess, given a little bit of a background into why and how I got into the space, covering some of the detail that Becky missed out, including failing 1 year at university. But here I am, back. I'm doing okay, I think. So what my aim here is to kind of walk through, I guess, the research that I've done across my PhD, my postdoc, and then on into my, I guess, my position here at Birmingham. PhD was around looking at the effects of very prolonged sustained exercise. We used adventure racing as a model to study that response in humans, and really to try and explore the limits of ultra performance. So this is a self-regulated performance, quite a unique scenario where you're working with athletes who are trying to win a race in the shortest amount of time, and a unique opportunity to understand that stress, that strain, the consequences on performance, our physical capacities, as well as the mechanisms that underpin some of those changes. So within my PhD, I had 3 studies. 2 of them were chasing athletes around different parts of New Zealand. The reason why 2003 was quite useful was that it was around Otago, Eastern Otago, with the university sitting in the middle, so a good opportunity for us as scientists to base ourselves in our labs a little bit while they went out and raced. 2004, we followed up with, I guess, following a race which was on the west coast. So Greymouth was where I was on the outdoor recreation course. Again, tracking these athletes to look at what was going on. Then the 3rd study that we did was to really focus in on that first 24 hours, which was a really key period in terms of how the races regulated their pace, and that became a real focus for my PhD. And here we are. So we did that. We set it up in the lab, so the athletes would go in and out of the lab, loop around for 7 hours on a bike, or 5 hours up in the hills, coming back into the lab to have those standard measures again. So quite a fruitful PhD, a wonderful opportunity to collaborate with Jim's friends and colleagues. Examples there, Jon Hallier, that some of you will know, and Nat Anglin, who's a reasonably high profile sports doctor in New Zealand. Looking at, it was a collaborative thing, so my input into this was to support Jim, because he wanted to race and he needed someone to support the research, which was how I first got involved. So at the end of this, I got another really neat opportunity to, I guess, write a review which sort of summarised all our work and that in the literature, and that was with Ralph Goldman, who is in essence the godfather of environmental physiology. Set up the military ergonomics division in the US Department of Defense. So yeah, that was a wonderful opportunity to work with such an esteemed person in our field. So my PhD was really, I guess, focused, the things which were particular to my PhD were looking at that intensity strain and the consequences of that. 2 people that I should mention in here, Craig Palmer and Carl Bradford, who were instrumental in helping me with gathering the data, who've gone on to do some good things, working particularly with New Zealand cycling. If you're a cyclist, you'll know that New Zealand cycling is quite strong. When they were here for the Commonwealth Games, our team did quite well, and here's 2 of my kids wearing some gold medals, which was quite a unique experience for the kids, and cool. If I had to summarise my PhD in a slide, the key findings were that humans competing in ultra-endurance exercise can settle into a race sustainable pace within our first 24 hours. Doesn't matter where that race is, what they're doing in terms of exercise modality. It seems to be a constant in terms of that pacing strategy. And that there's this uncoupling between our perception of effort and that workload. So heart rate stays the same for the same standard workload, but that feels harder. And that's linked to some pacing strategies and some brain regulatory processes that are going on Metabolically, we see a big shift towards fat utilization. We saw that at 100 hours. We saw that at 24 hours as well. So a very robust finding. So I guess this is my thread to regulation. It's all about the brain. The model that I used within my PhD was around the central governor. Tim Noakes is a little bit controversial, but he's not the only person that talks about the brain being important in terms of exercise. And another thread to the work that I've been doing, it's been really neat to work with Chris and Neil Dalloway, looking at brain endurance training. And again, that's it's the same fatigue, I guess, concept. And so it's been neat to sort of revisit a lot of the same literature that I used in my PhD while working with Chris and Neil. So we followed this up here. It was a neat opportunity to run a study out at Raymond Priestley Centre. And again, we did this, what happens in 7 hours, in terms of limiting it down as to the same shifts and changes happen within 7 hours. And we saw this similar shift in terms of our heart rate and perceived exertion uncoupling, and the same shift in our fat utilization. So this was a really cool way to sort of, I guess, translate what I've been doing in my PhD to a neat and a special environment here in the UK. Part of the premise of that was to run a pilot really to try and see how we could get our students, our sports science students, back to Coniston. And Becky's now leading this practical, which is now embedded within our scientific and professional communication module. Very much it's about the students exercising in that environment, understanding how to measure, work with heart rate, work with perceived exertion, some of those mood parameters to understand, I guess, something different from what they may be used to in the context of exercise and health, and to get them to think about something broader that they can apply to clients they may be working with as they move forward. So that's been a really neat, I guess, a thread through from my PhD and my outdoor education background to be able to do something like this with our students here. I guess more of an education context. But we're hoping, just putting the heat on Becky here, that she needs to write the paper from all the data that we're collecting. Okay, I think we're sort of on track time-wise. So that's my PhD. That's the link through from that work into what I'm doing now. Now, I guess, covering what I did particularly with in my postdoc, working with Phil. Phil's a great guy. Two important messages that I always like to think of that I learned from Phil was, one, don't let the politics ever get in the way of what you want to do. Phil can be a polarizing guy, especially with his admin team and senior management. But yeah, he was determined, and I think that was a really useful trait for me. Hopefully, I'm a little less bull in a china shop sometimes than Phil was. And the other statement you always hear from Phil quite often is, what could possibly go wrong? And it turns out quite a few things. But he had the likes of myself and others that would tend to tidy up behind him as he went through. So yeah, as I say, what I'm going to try and do is go through the work that I did, started, I guess, in my postdoc, which is sort of flowing through to where I am now. So this was very much the start of my journey, exploring the regulation of brain blood flow. We looked at a number of different physiological stresses: orthostatic stress, exercise, heat, and hypoxia. And I've underlined those because they're the ones I'll focus on as we move through, and in various populations, young and old, and also conditions of sleep apnea. And that's, I guess, the figure up here. So Phil and Jim and Keith Burgess, who is a sleep physician based in Australia. And I did a lot of work with him through my postdoc, including time over in Sydney, working in his sleep clinic, looking at sleep apnea in patients. Suffice it to say, this was a busy time. This slide is particularly for Jacob, to sort of show you, you are busy, I get it, but I also understand. This is just 2 weeks in a block of work that I was doing at the time. I think in that year we ran about 13 separate studies. About 7 of them were running all at one time. My job was to try and coordinate that and get people in the lab at the right time, as well as collect all those data, or data, however you want to pronounce it. So it was a busy time. It was also a busy time at home. We had our first two children, Ruby and Molly there on the left, and Henry there on the right. That came along and amongst this madness that was going on. Looks like many of you have actually been in some studies of mine, so you'll know what this technology is, but I thought I would share because this is I guess, what I'll talk about a lot as we move through. So measuring brain blood flow or velocity, there's lots of different methods. I came here with this technique. This is a video shot by Sam Weaver, actually. Thanks, Sam. It shows, I guess, we're getting beat-to-beat blood velocity. This is an index of blood flow that's moving through our vessels. So it's really useful in the context of doing this beat-to-beat changes. It's robust. It's easy to use. You can do it with exercise. You can throw people in water. You can take it up mountains. It's a pretty useful technique. The other key, I guess, thing from a theory is to give you an idea of the regulation of brain blood flow physiologically is quite complex. It's a tricky business. And particularly when you're putting physiological stress through the system, like with exercise or heating or hypoxia, all these different mechanisms interact into play. And therefore, when you're measuring things, you need to be measuring all of these at the same time so that you can understand things, understand what's happening. So I'll put boxes around the two key mechanisms or factors that I'll spend a bit of time in as we go through the rest of this. So work that I've done, some of the key studies that we did with Phil, particularly looking at, I guess, this blood pressure relationship, a number of different studies. One that I led and I'm particularly proud of is the work which is challenging something which is quite I guess, a dogma in the literature, challenging this Lassen curve, which stated that regardless or across a wide range of blood pressures, brain blood flow is very stable. Clinically, this is what they rely on to manage cerebral perfusion. They believe that a big drop in blood pressure is not a big deal because they think the curve autoregulation will take care of that. What we did is we manipulated blood pressure and we showed how pressure passive it really is. So it is really important to manage blood pressure if you want to maintain cerebral perfusion. So we challenged this. Again, this is one of the first studies, or perhaps the first experimental study in healthy people that, I guess, challenged this dogma, this old concept. And there was an updated review that came out in 2014. Which has now been cited over 1,000 times. I think that's off the bottom of the screen. You might not be able to see. But yeah, really proud of the work that I was involved in that led to that. In terms of the work that I guess I've done linked to this concept, one of the earlier studies that I did with Anna, Doug Carroll, with a PhD student, Ryan Brindle at the time, was look at psychological stress and how that manipulated brain blood flow. And we saw the same thing. You push blood pressure up, whether that's and through this scenario, through psychological stress, we use the famous PSAT test, which is a fun tool that's used often here in Birmingham. And we showed, again, that same thing in terms of you push blood pressure around, brain blood flow moves as well. And it's not because they have a disease state. It's a normal phenomenon that happens in healthy people as well. So I guess that challenges and makes the clinicians or people consider how to monitor brain blood flow and what to be careful about in a clinical context. So this work was really key for me, I guess, to get a footprint or I guess a standing in this space. And I've been part of the Cerebrovascular Network, or CARNet, been part of a few topical reviews, I guess, to try and address this dogma, and also been part of some of their white papers, consortium-led papers to talk about, I guess, key topics in our field. I've led in both of these the two recommendations or topics around how to use a multimodal approach to do this. So TCD are very much this camp, MRI, and even NEARS are in their own camps. One of the benefits and strengths of being here is I've been able to bring those things together thanks to some amazing colleagues, which I'll talk about in a little bit. So yeah, for us, through this network, I've done a couple of virtual seminars which I guess address these key topics that I've been interested in, that I guess have laid the foundation, I think, for why I guess I've been made professor in the context of the work that I've done, I guess, to shift this field forward. Okay, so I guess that's the mechanistic regulation, basic science, nerdy stuff that people get quite excited about. It's cool. But I guess being a sports scientist, an outdoor educator, I like the applied stuff as well. And I guess the best example of that is doing high altitude research. So as part of my postdoc, in fact, within the first month of starting a real job, I was off to Nepal to spend a couple of weeks up at high altitude doing science with a technique I knew nothing about or really how to do, but I got to go on an expedition. So I'm really lucky. I went on a couple of expeditions with Phil. These are, I guess, a unique and exciting experience. As Phil writes about it, this is a unique opportunity. So you tend to pack science in, your experiments in, and this is an example, again, of 3 weeks. This was the 2012 trip that we did that I actually led in terms of the management and the running of this. And we had 7 or 8 different studies with 7 or 8 different PIs with all the same needs and demands, that their science was the most important. So yeah, we're doing lots of cool science, but it's more than just a scientific expedition. Some of the skills that I picked up through this, has really helped me in the work that I'm doing now, particularly in some of the bigger consortiums that I'm involved in to help manage, and I guess, those competing demands. On this particular trip, I actually had to have my birthday, which was up there, which was fun. So even at 5,000 meters, you can have a birthday cake. Sadly, on the same trip, on the 28th of April, I missed my son's first birthday. So yeah, there are consequences sometimes, sorry, to these things. But yeah, there's a lot going on. So just to sort of touch on some of the work that I led was really, I guess, looking at changes in blood flow, how that adapts across a 2-week block. So that was, I guess, the paper that I led. We're also interested in how that happens. So looking at the ventilatory or the breathing sensitivity that you get in that environment. Then we manipulated it around with different pharmacological agents. Again, both of these are about changing brain blood flow, looking at that relationship, that causative effect of brain blood flow on breathing control. Ultimately, because we're interested in how that might affect sleep. So going to altitude is a wonderful model for studying sleep apnea, which I mentioned. So you can sort of see in these photos, a big part of what we did was about assessing how important brain blood flow is in the context of sleep apnea. So we had a couple of dramas with that particular, from an experimental study design. We had a couple of confounding factors, so we had to go back in 2012 to repeat that experiment, but do it without those same confounders. So we changed entitled CO2, which is an important regulator. So we weren't sure, was it just the fact that we changed the concentration of carbon dioxide in our blood, which has a direct effect on our breathing control, or was it because we improved our brain blood flow? So we went back, and this time we changed brain blood flow. We increased it without changing carbon dioxide, and we decreased the sleep apnea index. So happy days. We proved that brain blood flow has a direct effect. And the work that I was doing in Sydney with Keith was to then translate that into a clinical population who had obstructive sleep apnea. So to see whether that was a useful way to treat that. What I thought I'd do is show you some of the data that we collected, just so you kind of get an idea. Again, this is a measure of brain blood flow. This is what sleep looks like, awake and then going into stage 2 sleep. Andy, you'll be excited by this. With brain blood flow, and then we go to altitude, you see this increase in brain blood flow just while we were awake, and you see this real oscillation that's going on. This is a 5-minute block of brain blood flow, and you can see things are oscillating around. And as we spend time at altitude, brain blood flow starts to come down, this oscillation remains. And in fact, when you look at the apnea, it goes from 77 events an hour up to nearly 120. So you stop breathing nearly twice every minute when you're at altitude. And these are in healthy people with no other underlying pathology. So that's to give you a real crash course and why we're doing that. One of the cool things that I did from a research nerdy perspective was to pull our PSG data, which is all the sleep stuff, and link it in with our cardiovascular hemodynamics. So we've got our blood pressure and our brain blood flow. And for me, this was a really important moment in terms of why I thought there was a link between sleep, cerebral blood flow, and acute mountain sickness. So when we're asleep, our oxygen saturation is bouncing around between 80 and 60%. So if you go out to A&E today and you turn up with anything at or below 90%, they'll hit the red light and they'll admit you. So awake, it's around at 5,000 meters, it's about 80. So it's quite a stressful environment. And when you're sleeping, it really dips down. And interestingly, in the morning after sleep, you feel worse than you do at night. So I think this is, I guess, a real premise for thinking about mountain sickness. Is sleep related? Is it about these oscillations that are going on at night? So a thread into the work that I'm doing here, the Birmingham Medical Research Expeditionary Society. It's one of the oldest societies that does high altitude research. The first email that I got on my inbox when I arrived here in 2013 was from Alex Wright, asking me to join the society, come and see their meetings. Joe Bradwell is, I guess, the president, the patron. Yeah, I guess he started it back in 1978. So I've been very fortunate to go on, carry on my expedition science with these guys. And through this work, the BMRES has funded Kelsey's PhD and postdoc and research fellowship, which is carried on. And we've gone on and done this work, and we've collected lots of urine, we've taken lots of blood, had lots of fun times at altitude. But this was a nice link for me to think about. So this is a picture of me in 2012 walking up to our lab, and I was collecting pulse oximetry data with the thought of, could we use this? Is this part of what's going on, why we feel sick? Is because how much people desaturate? And does that level of desaturation, does that drive mountain sickness? Well, I never really did anything with that data, or those data. That became a key part of Kelsey's final PhD, which she then collected some more data, done some amazing work with the data that's been collected at night in terms of its analysis. And she's showing a really exciting link between the oxygenation saturations that are going on during the night at a lower altitude is predictive of how people are going to go at higher altitude. So before people get sick, you can see it in their sleep. And I think that's a really useful tool going forward. Kelsey went away earlier in the year, and the expedition she led collected data off people just walking up to Everest Base Camp. She had over 200 participants. So some really exciting work that's coming out of that. We're okay, we're still okay. In terms of hypoxia, it's a really neat model to work with. So coming here, one of the exciting things when I came and found out about what was available was the technique and the system that George Balanos has got. So it's got a clamping system which allows you to manipulate the blood gases in your body very precisely and maintain that. And we've done some work with George looking at the influence between hypoxia, hypocapnia, so changes, so you breathe more, you get rid of CO2, that decreases blood flow as well. So is it hypoxia, is it hypocapnia, is that what's affecting brain function? So we were able to show that even in the context of normal oxygen levels, if you decrease carbon dioxide, you also have an impairment on your cognitive function. So some neat mechanistic stuff. This is kind of where I started working with Hamid Degani. He looked surprised. He probably didn't know this is what was going on. But yeah, so Hamid is a NIRS man in terms of working with optical imaging, near infrared being one of those. So this is a technique that I started using in Phil's lab in New Zealand. Very much knew how to turn it on, collect data, lots of data, and think I know what it was about. Working with Hamid's been amazing in terms of understanding actually the physics that's going on behind this technique. So we've done quite a bit of work collaborating with our colleagues, clinical colleagues in neurotrauma, where we've looked at how does a non-invasive measure, which you stick on the head, how does that compare with direct measures in the brain? The different devices that are out there on the market, does that affect the measure that you're getting? And giving hypoxia to people is a neat way to, I guess, simulate brain trauma acutely. You return it and they're fine. And I guess this is what this figure shows us. With different locations and different systems, you have a real range of numbers. These should all be measuring essentially physiologically the same kind of thing, but we have quite a big range in terms of the number that we get. And that's a problem when you turn up roadside, stick this thing on someone to understand, particularly for the brain, what's the status of the brain? Do you infuse fluid or do you withhold it? Because if you get it wrong, you can do some serious damage. And that golden hour, that first golden hour, is really important in terms of managing that trauma. So we did some mechanistic stuff. Dr. Dave Davies, we injected some phenylephrine into my forehead and a few others. That's what's going on there to remove the extra cranial blood that was in the skin, to see if that was influencing the signal that we got. Did some Valsalva maneuvers, done lots of work around that as well. This is another neat tool to use. And what we showed is that actually it doesn't have a huge impact, particularly when you're doing a big sledgehammer physiological stimulation like this. And then I guess the Hamid's a real passion is for trying to improve the quantitative quality or accuracy of the measure that we're getting. So I supervised Mike with Hamid. I had lots of meetings where I understood nothing about what was being said, apart from we could give them hypoxia. But yeah, a really neat way, all I guess with that idea of improving the quality, accuracy of this, which means that we could have a decent measure in the community, whether that's roadside or in a GP clinic, to understand the health of the brain. And that's, I guess, an ongoing challenge that we're still working towards. So again, hypoxia, a really neat way to challenge the brain. And for me, some of the work that I've been doing now is around how do we actually measure that accurately in the brain. And then I guess the last topic within my postdoc to talk about really is the regulation of brain blood flow during exercise and brain function. So a key paper that came out of Phil's lab was looking at the relationship between fitness and aging and brain blood flow or brain velocity, showing that as we age, blood perfusion or velocity goes down, but you can offset that by being fitter. We showed, I was part of a study led by Chris Morrell, where after 12 weeks, we can increase resting flow, and we can also increase a measure of functional capacity of our vasculature. This is another key mechanism that we'll talk about a bit. Also showed a direct relationship between flow velocity and cognitive function, showing that the higher your velocity, whether that was a simple or a difficult task, the better or faster your response in a cognitive test. There's a younger looking Becky helping out on this project. Any opportunity. And the other thing that we did, we collected a bit of work, quite a lot of data in young healthy adults, and showed that this mechanism of brain blood flow regulation is an important mediator between physical activity, or the frequency of physical activity, and brain function. So this was a real key moment, I guess, or a series of studies that this is what I wanted to do and take forward when I came to Birmingham. So 2013 was when I moved over. I was very excited by the fact that there was already a house named after me. I thought this interview is an absolute shoo-in. How can I possibly go wrong? Having gone wrong 9 times, I think, before this, I thought this is the moment. So in my interview, this is what I said I wanted to do. I wanted to establish an independent program focused on optimizing the use of exercise to improve our brain health, and with a real focus around exercise. We settled into life pretty well. Before too long, our third and final its child came along. So that's Jay sitting up in the back there wearing his Maiden Mosley top. So we settled very quickly and enjoyed life here. A second objective was to determine what's the best test to assess this. And again, pretty early doors, I was introduced to Karen Mullinger, who's here, because I said, well, I want to write a little grant just to kind of test or check what my measure does, compares pretty well to MRI. So we can, so that was sort of the first little study. So we can compare these two main outcome measures. I guess this started a real theme for me around how do we measure it. So you don't need to look at this table and understand what's going on too much. Apologies for the green-red color coding here, but the idea is just to sort of show you, here's a bunch of studies in the literature that's used, that assessed this responsiveness measure. So you give people CO2 and their vessels dilate. Frustratingly, there's a number of different ways you can do that, which has different physiological effects. But so here's a bunch of studies which I guess doing that via their different means, and they're assessing the effect on the vasculature using either TCD or MRI. And even within MRI, there's a number of different ways that you can do that. Two key studies that I guess focused our attention to try and understand this was a study in 2013 in masters athletes that showed with bold, MRI bold, this measure is lower in masters athletes, whereas we have previously shown using TCD and others, Damien Bailey, some work in Cardiff, has shown that the same measure as a responsive test actually is higher. And so we were wanting to say, okay, well, what test is best? Do they actually align? So that's been, I guess, a theme for the work that I've been doing. So Karen and I sort of teamed up, and Claire, my first PhD student, became our first PhD student, and working together to try and look at this. So this was funded through the Physiological Society, again, with this aim and objective to kind of address this question. 3 aims, we were going to nail this in a year, which I guess is laughable now when I look at it, because we're still trying to figure this out now, 14 years later. But Claire did a great job. We got a few publications looking at just a type of the CO2 test, then comparing, I guess, this responsiveness test and even resting dynamics between our two modalities to see what we were measuring, whether they made sense, whether they were comparable. And then we've recently-ish written, I guess, again, pulled together our colleagues across different perfusion. So there's Hamid, there's Karen, Claire, Katerina, and Kate Thomas from New Zealand, all with expertise and experience in our different measures, imaging modalities to assess the vasculature. So that was a neat time. Again, this is an experimental slide. So for Claire's PhD, we ran effectively 2 studies. The guiding principle, and we took 20 young, 20 or 15 old in the first study, with fit and unfit, sort of evenish split. Then study 2, we took 10 younger who were the fittest, and 10 old who were unfit, trying to separate the 2 groups as best we could to try and address this question. Our guiding principles, what we wanted to do was, with exactly the same physiological setup and stimulus across these 2 modalities, would we get the same outcome? We tried 7% CO2. Turns out it's quite full on. Dad can attest to that. He was one of our pilot subjects. He didn't enjoy it very much at all. And if my dad doesn't like it, as a rule, I usually carry on. No, but for anybody else, you think, right, now this is a bit full on. So we ended up just using 5%. That's why that figures like that. So what does it look like against the literature? I guess our findings, just to give you the context, cerebrovascular health declines as we age. Doesn't matter in the literature, whether that's MRI based, using different, so this is perfusion, tissue perfusion, this is transit time, so it's sort of a measure of how fast, or how long it takes the blood to move through the brain. You see perfusion go down as we age, and we see transit time get slower. And similar here, so this is our velocity measure, which gets slower as we age. There is some evidence in terms of the positive fitness effect, as I've sort of talked about this work out of Phil's lab. I think I'm one of those dots, hopefully a dark one, sorry, an open circle one. We see this increase in our velocity. We also see structural changes, and that's probably important to think about in the context of I guess, a wider question. So Claire's key question was, how comparable are these things between aging and fitness? Produced some of the first data that showed, with the same people doing the same technique, pretty robust fitness effects. Sorry, you can see the aging effect here. Perfusion, it's lower-ish, not quite significant, but it is a small group where you see perfusion's lower in MRI measure, and we've got slower velocity in our Doppler measure. So the aging effect seems pretty robust in the same people. Fitness is a little bit messy, not quite as clean. And I'll talk about that more in a bit. And when you then correlate the two measures, what we see is that when you look at perfusion against TCD, there's very little correlation between a measure that's at the tissue and the capillaries versus the Doppler, which is picking up the velocity through a conduit vessel. So even though in the literature they're supposed to be measuring the same thing, they actually don't correlate. Whereas if you're looking at transit time off MRI and the velocity from a Doppler measure, the physics are essentially the same. And fortunately, it makes sense that those numbers do line up. I think I'll be reasonably quick through this, but just to sort of say that I guess the key findings, so that was resting flow or velocity measures, perfusion measures, this responsiveness measure that we had, what we saw are completely opposite depending on the modality that you use. So this, I think, was really useful in the context of helping us understand why the literature is so conflicted. When you take the same people, use the same technique, put them in these two different imaging modalities, you get a very different story depending on the imaging modality that you use. So that was helpful in the context of us understanding why the literature was so conflicted. So despite there being resting agreement between our two different modalities, this measure of responsiveness, or this functional responsiveness, is very different. And it's probably related to the fact of where we're measuring perfusion. So with Doppler, we're measuring it in an artery, conduit artery, whereas BOLD, we're measuring it in the venules, sort of at the other end of the vascular tree. So potentially, using the combination of these techniques is a useful way to look at maybe different parts of the arterial tree in terms of how they're affected by disease and how they also respond to an intervention. So we're taking this idea forward, and Asha, who's part of the PREDICT team, this is going to form part of her PhD across, again, we've got MRI, we've got Doppler using this technique, but this time in MTBI patients to try and understand, again, in a more of a disease context, is there some agreement with this measure? And I guess this is our concept. I guess, yeah, the principle that allows what I'm interested in, instead of using separate techniques in isolation, we should be combining. This is the argument that we're making, combining these methods to better assess brain health. Rickson's also joined the team here with Hamid, and he's really passionate for, again, improving the accuracy. And in terms of answering a question of why I'm here, there is, I don't think, anywhere else in the world that can do this, that can address this question with all these different modalities, with the range of expertise. And I guess I put myself on this side of the equation, but working with Karen, Hamid, and Rickson allows us to really address this in a unique and a novel way. So yeah, we put this together in a text. In the interest of time, I'm going to skip through these slides, but this was an opportunity to look at the fitness effect. We do have things to do, places to be, but we took an older population, we trained them using our best possible imaging technique that we had. We showed that with a 6 months intervention, measuring perfusion well, actually it goes down. So I guess in the context of this messy literature, some of which it goes up, some of which you don't really know, some of it goes down, our FAB project, I guess, is consistent with the fact that perfusion with increases in fitness decrease. It's messy, it's complicated. There's lots of confounding effects that are going on here. One of which could be the timing of when we're measuring this. One thing which I'm really excited about what we're doing next is in, I guess, our perfusion context, we do a lot of work around this. We measure blood flow, right? In the context of what's happening with training, no one really is looking at this side of the equation. And there'll be some muscle physiologists in here who think that's absolutely crazy. So we've been really fortunate. I was like, oh, physiologically, we should be able to, this is probably what's going on. Maybe that explains why perfusion goes down, you're getting more efficient in the tissue. So I said that to Karen. She goes away, does her amazing physics thing, talks with her colleagues, and we've now got a way to measure that in the brain. Jack has finished a study and working on a publication to show the influence of that. Okay, 10 minutes, I think I can do this, easy. Right, so the last one is just to come back and talk a little bit about some of the work that we've been doing to, I guess, address this primary question that I had. But before I could do that, I really wanted to make sure I could measure it properly. So that's why I've effectively spent 14 years trying to understand what the hell are we measuring? And can we, if we do this better, optimally, we can actually truly, validly measure the effectiveness of any intervention. So that's why we kind of got stuck on that. And nevertheless, we've been trucking along, doing a little bit of work in this space. And this is, again, part of Claire's PhD was to, I guess, write a review around using exercise to improve brain health, particularly different types of exercise, focusing on a key mechanism that we think is important in terms of improving brain health. And that's the movement of the blood. So when we exercise, blood flow goes up. That mechanical force of the blood moving through the vessel releases good things that improve nitric oxide, for example, that improve the ability of the vessels to operate. So a question that I guess I had is, well, there's lots of different ways to do exercise. Does this affect how that, I guess, that key mechanism affects the brain vasculature? So I've done a series of studies working with a number of masters or even undergraduate projects, and Sam Weaver, who's kindly come along today to I guess, observe what it looks like. What does blood flow look like, or velocity look like, when we're doing these different types of exercise, either running or cycling, and it is different between these different modalities. What does it look like when you're doing high intensity or interval types of exercise, either all out types of approaches or a clinical based HIIT approach? What does that mean in terms of the signal? So we take blood to understand, I guess, what's being released, working with colleagues, and most recently Rich, who's doing some really great work. And again, I can run studies, I can collect data, I can do that, and then I give it to the person who knows some pretty cool biochemistry, looking at what's in the blood. Is that different between the exercise? What does that mean in terms of the stimulus to drive improved interventions? And all that information, the idea, the dream, is to then design the ultimate or the optimal exercise intervention that's going to improve molecular function, the hemodynamics, the structure of the brain, and ultimately improve cognitive function. And that's then where I'm then working with colleagues that know how to do this stuff well. And again, so a real collaborative, multidisciplinary approach. I guess that's the model of how I'm going across. So I'm only going to present one study that I've done on this, so relax. And this is very much Sam's work through his PhD, where we looked at the different blood flow profiles, so the cerebral hemodynamic profiles between, I guess, a HIIT protocol versus a continuous exercise protocol versus a sprint base. So these are the three main distinct exercise protocols that get promoted. Not a lot of work at this time had been done looking at brain vasculature. So these are our protocols in terms of a 30-minute continuous. So that's our public health guidelines that gets promoted. Here's a clinical HIIT model, 4-minute intervals at about 85% of heart rate max. And then here's a really exciting and fun all-out 30-second HIIT protocol. So measuring brain blood flow during that time, respiratory gases, so we can understand the effect of CO2 on that, and then of course taking blood as we go along. So in terms of the brain blood flow or blood velocity profile, increased from rest and then pretty much maintained across a 30-minute interval. And then we have different profiles for these two different interval-based exercises. And particularly the sit or the sprint-based protocol, I see a huge increase in the first interval and then a very much a blunted response. But we also have this fun little rebound response that goes when they stop the interval, there is like a rebound of the brain blood flow. And Jacob has followed this up with his master's, which has now become a PhD, work exploring some of that. So there is a different profile dependent on the different type of exercise that you do. And this is just within cycling. So what does this mean? Why do we care? So if we look in the blood, so BDNF, so this is a key protein that we think is really important in terms of improving brain structure, brain function. We can see with SIT, so the blue here, the sprint-based protocol, you get a much bigger response through that. It's similar, there's a VGS, a vascular growth, endothelial growth factor, another key protein that's important in terms of improving vascular function. We can see that that's elevated, that's important. The nice recent review which shows why this is important here is exercise driving these effects, particularly lactate, which improves or increases these key proteins, driving these key processes in terms of improving the structure of the brain, the vascular function, decreases inflammation, all of which are improving the function of the brain, either vascularly or cognitively in terms of our behavior. So very much our working hypothesis, our ongoing question, and this has been part of the FAB project, which essentially was a home-based intervention, which was sort of based around high-intensity exercise, is that HIIT is pretty good. It is important, and it looks like it's releasing greater or a greater increase in key neurotropic factors, which are linked to positive brain health. The challenge for us, and we think that's potentially being mediated through increases in lactate, is how to get that to happen without, I guess, some of the negative effects associated, maybe from a behavioural perspective, mostly in terms of getting people to do that, and particularly in populations that may not be able to do all our types of exercise. So this is what we're kind of ongoing. We've got a grant application at the moment where we're going to play around with some of these interval-based protocols to look at what's the best way to improve or increase lactate, because we think it's important in terms of particularly driving BDNF. Last slide. How am I going? Not too bad. Under the hour, yes. So I guess if I was to look at my research overview, very much about, I guess, human health, but particularly brain health, looking at mechanisms, looking at how that's applied, how we can apply that knowledge, and then applying it into a clinical context. I think I've shown some reasonable examples of the work that I've done and I guess is ongoing. So we can really understand what makes and maintains a healthy brain. How can we then optimize brain health using exercise, for example. I spent a lot of time trying to sort of figure this out. We're still working on it, but I think we've got a really neat, I guess, model or approach to understand, how what we're measuring is something useful, and therefore measure the effectiveness or the efficacy of any intervention that we do. Something I haven't really talked about, but work that I've got going on as well, but most of it's in its infancy really, is looking at treating or identifying a diseased brain. And a lot of work I can see coming, definitely, is around concussion and working with Dan at MoveWell with, I guess, I got a concussion clinic going up and a really neat research opportunity to move forward where we can improve, I guess, our understanding of concussion, the effects on the brain, but also support our athletes getting back into, I guess, university study and also sport, of course. So I've got, I guess, some thanks to do. I'm not sure if you're aware, but I've had a secret little competition going to try and publish with as many people in the school as I can. I think everybody on this list, I've pretty much got to do that, or we're close at some point. But yeah, for me, one of the most vivid memories I had in my first few months was just going around meeting and talking with people and getting excited about the work that we could do. Yeah, and it's been amazing to really, I guess, see some of that. The students obviously do all the work. which has been amazing. Colleagues in New Zealand, and I've bunched some important people. I'm sorry, I definitely would have forgotten some across to the rest of the world. And I guess colleagues in CHBH and med school, or CMH, or whatever it's called now, and particularly, I guess, at the BMRes, which has been great in terms of my applied hypoxic stuff. I have to acknowledge three key mentors that I guess have helped me along the way here. So here's Jim and Phil. This is in Kathmandu on, I think, our first trip. There's Jim just being leisurely laying back as he tends to be in normal life, and Phil and Greg Anson, who was a wonderful mentor through my PhD, a kind, wise person, just to help, I guess, control Jim and I in terms of some of the madness that we were planning. And I guess I've already shown you that often we still get to work with these guys. It's great and have good relationships, both personally and professionally. I have to acknowledge and thank my family, particularly mum and dad, for the support, encouragement through the years, particularly not losing hope when I walked away from Canterbury University and said, I'm never going back to university. Turns out I'm never going to leave. Becky, who's obviously been part of my whole research journey through my PhD, and now here. I've had a great opportunity, Dad being the age of the years, to be involved in some of our studies. So it's great fun, especially when I was younger and he'd take me running, the pain that he would give me to run a max test on him. You can see I'm having a great time. I think he's just finished. So it's great. And of course, Mum has always been a wonderful supporter. This is me in my PhD gown. So if anyone wanted to know what a Otago gown looks like, that's it there. It's not what I tend to wear at graduation. And then finally, my family up the back, as you've sort of seen, so kids, and particularly Kristen. So she's been, I guess, my PhD journey, strange enough, turned around at about the same time that she and I got together. Causative, correlative, I'm not sure, probably causative, I think. So she's been right through this journey with me. This is a picture of her proofreading my thesis at about 1:30 the day before it was due. I think 9 o'clock. I think I got an extra weekend. Time management, I guess our version of that are very different between the TAPSILs and the lectures. But yeah, just a huge thank you to the support, the love that you've given me, and enabled me, I guess, to be able to do what I've done, which has included being away quite a lot when the kids were little. So yeah, thank you for listening. I think that's it. Yeah, I'm done. Thank you.
Pretty good. Good evening, everybody. For those of you that don't know me, which aren't very many people, I don't think, in the room, my name's Sarah Aldred. I'm head of school of Sport, Exercise and Rehabilitation Sciences. I'll add my very belated welcome to those that we've already heard. You're very welcome here tonight. It's great to see so many people. Don't do that. Inaugurals are a very special occasion. Obviously, it's very rare that you get the chance to actually really revisit all of the different, I guess, stages and steps in your career and the things that have kind of pulled that together. Things make sense for me now. I now know why you like Coniston so much. I first met Sam, actually, it was a really dodgy internet call. Yeah, where I think it was the middle of the night. Sam was in his pajamas. We didn't actually know that he was in his pajamas, thankfully, which was a pre-interview for the interview for the job. But I guess to pick up Sam's thread, or threads of what we've heard about tonight, working in the field, working up mountains, collecting data. We saw a lot of data. We saw some whiz by that we didn't get to hear very much about. But I think what Sam probably didn't talk about so much is how difficult it is to collect quality data in those kinds of environments. And he just assumed that we knew that that was all dead easy, but it's totally not. So I think coming from trying to understand mechanistic patterns and the mechanisms of how things work in those settings is really challenging. So that's, I guess, something I wanted to highlight. I think the other things that come through for me, obviously the brain, and I'm absolutely already sold on the brain. That's also my thing. So it's great to hear so much about the brain and about brain health and being really reminded why that's really important. But also how difficult and challenging it is to actually work with the brain. It's not accessible to us at all, which is just, yeah, makes life very difficult. For those of you that are like muscle, it's dead easy. You can just dig a hole in it, it's fine. Can't do that in a brain. And finally, I think collaborations. I mean, the list of people is crazy. But that's very much Sam. That's how I know Sam. Sam collaborates and is very collegiate. Maybe add the third bullet point to your, why academia is like the best dream job is the fact probably that you get to work with so many people, learn from so many people, and we all learn from each other. And I think that's one thing that really comes through in Sam's work. He's very keen to include others and to support others. And actually, I think the final thing I'll say is that whether Sam is educating students or in a lecture theatre, or whether he's talking about his research and sat in a research group meeting, the passion and the energy is equal, which I think is not always the case in academia. So that's really special. Last thing, two last things to say. Second to last, if you haven't had a chance to sign the poster down here at the front, please do. It's a memento that people get to take away. I saw your signature. That was very good. So please sign that, and Sam will get to pop that on his wall. And then the final thing is please join us back at Sportex for the after party. Please join me in thanking Sam and congratulating him. Good.
Oh, yeah.